How's everybody doing today? Good, good, good. So today this lab is it's a great lab actually. So it's relative reactivities of some alkyl halides, and so what we're going to be doing is pretty much comparing Sn1 and Sn2 reactions, but actually in the lab. So we've done this on paper before. Currently still doing it, right? So what we're going to do today is take a look at some of the factors that affect Sn1 and Sn2. So, for example, when we're trying to like categorize the different factors for Sn1 and Sn2, we look at the first thing, right, alkyl halide. The next thing that we might look at is the nucleophile, then the leaving group, and then the solvent, right? So these are obviously conditions that'll promote Sn1 or Sn2. Depending on what they are. And so what we're doing today is we will have the same 10 substrates for Sn1 and Sn2 conditions. So the Sn2 conditions are going to have, of course, our polar aprotic solvent. We're going to use acetone today. And then our choice of nucleophile is going to be iodide. So what we're doing is adding sodium iodide as our source for the nucleophile. Iodide is negatively charged, it is a nucleophile. And then since the solvent and the nucleophile are going to be the same, the things that we want to focus on when we're trying to like kind of analyze the outcomes and assess whether or not that was the projected outcome, then what we want to do is look at the other factors. So again, solvent is the same, and the nucleophile is going to be the same. And so what we're going to look at is the leaving group as well as the, why am I tripping right now? The alkyl halide. Oh, it's a good start, y'all. So that's for Sn2. We're going to do the same thing in terms of like what we're looking at for the projected outcome for Sn1, but obviously our conditions are going to be different. We're going to promote Sn1 by using a polar protic solvent, and so in this case it's going to be ethanol. Okay, but in addition to ethanol, what we actually have is a silver nitrate. Right? Let me just double check for sure. Yeah, it's 1% silver nitrate in ethanol. So the purpose of this is basically when we're doing this particular reaction, what we're looking for is a precipitate. So that precipitate is going to be silver halides. So remember from general chemistry, silver chloride, silver bromide are not soluble in water, but they're also not going to be soluble in our ethanol solution. And then this is going to be a driving force, right? Le Chatelier's principle, if you have one of the products, the silver chloride, precipitating out, it's going to drive the reaction to the right, okay? And then the same is actually going to occur for that Sn2 reaction. So since we have, we're using sodium iodide, which is soluble in acetone, great. Our leaving groups will be the chloride and the bromide, and sodium chloride and sodium bromide are not soluble in acetone. So those will form a precipitate as well. Again, driving the reaction forward, okay? And again, this is what we're pretty much looking for when we're trying to determine if a reaction occurred. So remember, the precipitates can look different depending on what's going on, right? So it could look, the solution might just get cloudy. The solution could form obvious chunks, or it might just get, it just depends. Like the precipitate, in other words, is going to look different. It's going to present itself differently. So we just need to make sure that when we're doing these reactions, we make the best observations and notes as possible. So what I want you to do throughout this video is literally write down anything and everything that you see, whether it's a color change. If it's a color change, I might mention that to you because it might be a little bit difficult to identify that color change, or at least observe it. And in the video. And then if there's a precipitate or cloudiness or whatever, what I'm going to do is just kind of hold up the test tube like that so that it's visible to you, and so that way you can make your observations. So what we're going to do first is the Sn2 condition. So what I've actually done is set up 10 test tubes right here, and you can see that I've labeled them numbers 1 through 10. So here's a 5 for you. I labeled them with a Sharpie because it doesn't come off very easily. It does come off. You can hit it with some isopropanol or rubbing alcohol or acetone or whatever when you're cleaning your dishes, and it'll come off. But we may or may not be placing these test tubes in the water, and so I just want to make sure it doesn't wipe off. Okay. So what I did here was I placed 2 mils of 15% sodium iodide in acetone, and so our nucleophile is in here, as well as our polar aprotic solvent. And what we're going to do is just add 4 drops of, let's say, our substrates. So this first one that I'm going to do is 2-chlorobutane. It is a flammable liquid, so obviously we want to be careful, but just 4 drops. And then we're going to make our observations. So if nothing happens, maybe like after 30 seconds to a minute, then what we want to do is obviously record those observations and set that aside. And then once we've done all 1 through 10 and we've set aside the ones that don't react after about a minute, and then we've set aside the ones that do react, we've separated them. And so the ones that don't react, what we're going to want to do is place those in a 50-degree water bath. And of course, higher temperatures is going to allow us to overcome the activation energy if it's higher, right? And so we want to see if the reaction occurs after placing it in a water bath, and then obviously record the approximate time it takes for the reaction to occur, or if it didn't occur at all. Okay, so literally write down anything and everything you see, and I'll try my best to kind of get the video on all the action. Okay, tons of action today. So again, putting just 4 drops of 2-chlorobutane in the first one, looking at it, swirling it. We're going to record our observations. Let's say a precipitate did occur. Then we're going to want to record that and approximately how long it took. And then after that, we're going to set that aside, right? That reaction's done. And then, well, let's just go. Let's go. We got this. You got it. So this first one right here. Oh, and I do want to mention that I already set up that water bath because I'm an adult on a plan ahead, because you don't want to get to the point where you need to use the water bath and then wait for it to warm up, right? So, all right, so here's the test tube number 1, which is 2-chlorobutane, okay? 1, 2, 3, 4 drops. Now, what you want to do when we're actually performing these reactions is approximate, or you decide if the reaction is going to occur or not. With or without heat, doesn't matter. On paper, is the reaction going to occur? And so, of course, you're taking into consideration the substrate, and then whether or not that's likely going to occur in an Sn2 reaction in this case. And if it does, let's say like methyl and primary, those occur much faster than secondary, right? And so when we're recording our approximate time on how long this took, then we also want to see if it goes along with that trend as well. Okay, so we're applying everything we know about Sn2 into these 10 reactions right here. Okay, so far this is 2-chlorobutane, and I'm just gonna tell you, I personally do not observe a color change. Okay, so set that one aside for now. Now what we want to do is, the next one is, number 2 is 2-bromo butane. All right. Let's see. So, same structure, different leaving group, right? Hit that with 4 drops. 1, 2, 3, 4. Whoa. That came out fast. There we go. Not a thing going on. Doo 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 doo. All right, so next one. Okay, so number 3 here. Number 3 is going to be 1-chlorobutane. Okay, so we've got 1, 2, 3, 4 drops. Just keep an eye on that for a little longer. All right. So, set that aside for now. Now, the next one is, what do you think it is? 1-bromo butane. Number 4. Okay. Okay, no. 1, 2, 3, 4. Can't tell. This one looks a little bit more yellow, but it is difficult to tell. Let's hold them all up together. This is 1 on this side, and this is 4 on this side. So you can kind of see the difference in color. Oddly enough, the first two substrates are yellow, but the second 2 are colorless. But it looks like the first 2 reactions are colorless, and the second 2 are yellow. So again, just an observation. So here we go. Now what we've got is number 5, which is tert-butyl chloride, also known as 2-chloro-2-methylpropane. Okay? 2-chloro-2-methylpropane. Yes. So, aka tert-butyl chloride. It's very similar in structure to the tert-butoxide. Remember, that's the chicken foot. 1, 2, 3, 4. And boom, 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 boom. Oop. So this one is a little cloudy. That's the bromine one. I'm sorry, that's number 4. That was 1-bromo butane. That is looking cloudy, right? Not sure about that one. Okay, so let's see here. What we've got is number 6, and this is crotyl chloride. Okay, crotyl chloride. Four. What you think? Write it down. It's much too strong. to let it go. All right, number 7, benzyl chloride. Bam, bam, bam. We got benzyl chloride in the house, y'all. Let's see what it does, what it is, what it isn't. Sorry. Oh, hold up, wait a minute. Let me get my caps up in it. All right, sorry, I had to get myself situated. Benzyl chloride. Super cool, super cool. 1, 2, 3, 4. I'm gonna go one more again, just because I can. That's, whoa. Swirly, swirly, swirl. All right. I think you've had about enough of that one. All right, so here's number 8. This is Bromo Benzene. Bromo Benzene. Bromo Benzene. 1, 2, 3, 4. 5th. 1, 2, 3, 4, 5th. Here we go. Well, we're on the topic of 1, 2, 3, 4, 5th. 5th. Dave Chappelle, fantastic comedian, right? Amazing. He was on that Netflix show with David Letterman. Forget what it's called, but I'm sure it's super easy to find if you have Netflix. Check it out. Super cool. Loved it. Liked it. Wanted some more of it. And then next, so we already kind of saw that, right? So hopefully you're multitasking as I am. The next one, number 9, is bromocyclohexane. Okay. Bromocyclohexane. 1, 2, 3, 4, 5. My hand looks like it's all swollen, like it got stung by an alien, really, because what kind of swollen hand is that? That's crazy. Y'all are ridiculous right now. Y'all are just silly. Okay, so bromocyclopentane. That last one, number 9, was bromocyclohexane. This one right here is bromocyclopentane. 1, 2, 3, 4, 5-ish. Let's see if I can get that to focus. Focus, Bromo Butane. Alright, so here's the thing. I'm going to run it back one more time. So here's 1, 2, 3. Seemingly no precipitate. So I'm going to set those aside. Here's number 4. So number 4, hopefully you guys wrote this down, but is 1 Bromo Butane. Do you think that looks like a precipitate? Okay, cool. So do I. Number 5. Doesn't look like anything. I'm going to go ahead and set that to the side. Number 6, which is crotyl chloride. That looks like chunky. Not really chunky, but it looks like some thick juice, actually. Kind of delicious. Number 7, That's benzyl chloride. That looks like some thick juice. Here's number 8. That's Bromo Benzene. Not a thing. Number 9. Samesies. Nothing going on. Number 10. So number 9 and 10 were bromocyclohexane and bromocyclopentane, respectively. Not a thing. Okay. So what we've got here is failure to react. So what we're going to do is throw these inside of a water bath, which I totally got set up right now. So let me show you as I move that camera real quick. So what I'm likely going to have to do so that you can actually like observe closely is I'm going to hold the camera. So I'm sorry, forgot to shake your hand. Earthquake! But basically, the only ones that aren't going to go in the water bath are number 4, 6, and 7. So, yeah, it's going to look a little complicated, but let's take a look. All right, so that, oh, you can't see that very well. That says 48. That's good enough. We got a hot water bath going on right here. I put it in a beaker specifically so that I could just go like, what's up, number 9? Engine, number 9. Set you in there. And then I would just kind of start the clock, you know what I mean? So let's go ahead and get everybody in there. We're gonna. So that's what I meant. I said complicated. Oh, I guess what I really meant was crowded. It's gonna get crowded in there, and we're gonna have to just kind of keep an eye on the individuals that kind of form that precipitate. So what I'm gonna do is kind of circle around, take a look, see what about this one right here. Maybe a little something. It looks kind of pretty though, I'm not gonna lie. And then yeah. So let's keep it going. So ideally we wouldn't have the tubes necessarily sitting right on the bottom of that beaker because it's like it's sitting on the hot plate, but it's not really enclosed, not really touching it too much. And also it's only like 50 degrees, so it's not too hot, but keep that in mind. And so I think when I don't know, I think I misspoke. In the beginning, we kind of wanted to keep an eye on the things at room temperature after 3 minutes to see if we had a reaction. And so what we're looking for is essentially we're going to classify in terms of rates of reactivity, right? And so the things that were fast, the things that were slow. So think about it like that. If it occurred, so the reactive halides, for example, give a precipitate within 3 minutes at room temperature. The moderately reactive halides would give a precipitate when heated, and the unreactive halides do not give a precipitate, okay, even when heated. So we want to record those results in our notebook, and then explain why the compound has the reactivity you observed, and then whether or not it kind of matches your prediction that I told you to make in the beginning. So I'm going to go ahead and say that this one right here, this, yeah, we'll leave that in there for just another minute or so. And then we'll take them all out, let them cool to room temperature, and then we'll see what they've got. Okay, so that was definitely plenty of time. So what we're going to do is take these bad boys out. One thing I also want to note that is we heated to, like, why did we only hit to 50? Well, first of all, remember that when you heat a reaction in general, any increase in about 10 degrees is approximately doubling the rate of the reaction, right? Super cool, fun little fact about that. But in addition to that, what we have is a solvent that does boil around there. So we don't want to go higher than the solvent's boiling point when we're heating it. So that's something you want to keep in mind whenever you're doing a chemical reaction. If the reaction doesn't occur at room temperature and you want to increase the temperature, is it going to require a lot? If it requires a lot, then you're probably going to want to choose a solvent that has a high boiling point. So, for example, like toluene it's like a benzene ring with the methyl on it. That has a boiling point of 110 degrees. So if I wanted to like heat the heck out of these, then I might choose that one. Okay, so not super polar though, so it's not an ideal reaction solvent for Sn2. But let's take a look at these ones and see what kind of precipitate we've got. Okay, so I'm not going to say anything. I just kind of want you guys to figure this out. Okay, so all I'm going to say is number one is number two is number two, and three is number three. Do it like that too. Here's number 5. That's what's up. Here's number 8. Okay, and here's number 9. And here's number 10. Snow globin. What's up, snow globin? And there you have it. So go ahead, write it down, take a picture, think about it. I encourage you to not only draw your structures out, but classify them according to alkyl halide. So like methyl, primary, secondary, tertiary, or like benzyl, or it's allylic or vinylic or aryl, etc. Okay, so watch the videos, the lecture videos. If you don't remember the general rates of reactivity, it's really important that you do. And then hopefully we observed that trend here in the lab. If not, maybe I made an error, maybe not, maybe you're not thinking about it right, maybe, right? Think about it. Super fun stuff. So now what I got to do is clean out these test tubes, and then what we're going to do is the Sn1 reaction. Same exact thing, so hopefully we can just run through it a lot quicker this time. And then, yeah, get on our way, right? So one thing I will say is that this particular, it's an Sn1 reaction. There's a little bit of water that's going to be in here, and the ethanol. It is supposed to be absolute ethanol, but what I'm getting at is I'm going to clean these, and I'm not going to get too crazy about drying them. I'm just going to wash them, flip them upside down, and then do some other stuff for real quick, and then be on my way. Okay, just to be able to move quickly. Because this is an Sn1 reaction, water is a polar protic solvent, and so like it's not going to be the end of the world if we have a little bit in there. Silver chloride or bromide are still going to precipitate perfectly fine in water, so it shouldn't affect the rate of the reaction. Yada yada yada. Okay. All right, so the relative reactivities of some alkyl halides. These are the 10 substrates in order. Going from top to bottom on the left, and then going from top to bottom on the right. So 2-chlorobutane, there's a structure. 2-bromobutane, there's a structure. 1-chloro and 1-bromobutane, the structure's right there. 2-chloro, 2-methylpropane, aka butyl chloride. Now those are all flammable liquids, okay? So they're hydrocarbons, right? So crotyl chloride on the upper right, as well as benzyl chloride, those are called lacrimators. And lacrimators are actually, here, let me write that down for you, lacrimator. And that's benzyl chloride as well as crotyl chloride. These are lacrimators because they irritate your eyes and they can cause tears. And so that is why they're called lacrimators. And this is one of the hazards that you want to write down in your table. Now, bromo benzene and bromocyclohexane and bromocyclopentane, those are also going to be flammable liquids as well. And anytime you're in a lab, you always want to just assume everything's toxic, and everything's flammable and everything's dangerous. And so that's what we're going to do here. Okay, so all these are toxic and flammable, and I also want to add in that lacrimator just for kind of some vocabulary in terms of some hazards that we need to be aware of. And there you go. So let's go ahead and start the reaction. All right, so just a reminder for the Sn1 as well as Sn2, we want to make sure that we're thinking about the structure of these substrates because the nucleophile is the same, the solvent's the same, and identifying the reason why a reaction would occur faster or slower. And then we're going to rank these according to high reactivity or mild or moderate. Mild and moderate being the same, and then also non-reactive alkyl halides. And so in addition to that, I want you to think about, like I said, the alkyl halide, was it tertiary or secondary, etc. You also want to think about the structure of the compound. For example, is there any particular strain in it already? And then how that strain might affect the rate of reactivity in terms of bond strengths, etc. So that's kind of just some guidance and moving forward for this particular reaction. And so now what we want to do is we're going to do the Sn1 reaction conditions. So we're using all of the same substrates, so compound 1 through 10 in the same order again. But this time what I have here is a solution of silver nitrate in here. And again, this is a 1% silver nitrate in ethanol solution. So this is the polar protic solvent. So that's going to promote Sn1. And then we also have, so I have number 1 right here, and then this is number 6. And so when it comes time, I'll put the ones that are in the back, 7, 8, 9, 10. We'll rotate this rack so that you have a better look at them. But what I really want to do is just kind of quickly add the substrates to all of these and then let you take a look at them for a bit. And then we'll kind of rotate this around, boom, like that, and then we'll move on. Okay, so let's see, was there anything else that I wanted to add? No, I don't think so. So, there was also leaving groups that I wanted to see if you kind of paid attention to in terms of classifying the rate of reactivity. Okay, so now what we're going to do is quickly and carefully move through these reactions. Okay, so sorry, I'm getting organized. Wanted to change things. All right, again, this is number 1, so I'm going to add 4 drops to it. You keep an eye on it. So let's see, this is 2-chlorobutane. 1, 2, 3, 4. And we're going to give it a little shaky shake. Shake, 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 shake. Okay. Now we're doing 2-bromo butane. 1, 2, 3, 4 ish. Boom, boom, boom. A little shaky shake. Wait, you can't see that. A little shaky shake. Okay, okay, no. Now number 3 is 1-chlorobutane. 1, 2, 3, 4 ish. Oop, there it is. 1-bromo butane for number 4. shaky shake. What you know about Sn2 or Sn1? All right, so this is number 5. We got that T-butyl chloride. Don't even need to shake that one, you know. Crotyl chloride for number 6. 1, 2, 3, 4, 5, 6. Whoa, simmer down there. Simmer down. Oh, okay. So benzyl chloride. Well, before we move on to benzyl chloride, because that's number 7, that's on the back. We're gonna go ahead and take a look at this again. A little shaky shake. Okay. This is number 2. Here's number 3. Do a little shaky shake. Number 4. Okay. And then number 5, number 6. All right, so we'll probably take a look at these when we come back, right before we start adding things to the heat. But here's number 7, 8, 9, and 10. Number 7 is benzyl chloride. What you think? 1, 2, 3, 4-ish. Hmm. 8. Bromo Benzene. This guy's doing something silly over here. Oh, it's because it's dripping down. Teehee. What you know? Bromocyclohexane. Number 9. That was probably too many drops, but don't worry about it, folks. Don't even worry about it. It's okay. You're gonna be alright. It's okay. Bromocyclopentane. Let's see what it does. 1, 2, 3, 4, 5. 1, 2. Whoa, simmer down there, bromocyclopentane. You got an attitude. Coming in hot, huh? Let's see what it is, what it look like. Okay. It's so chunky. Chunker. Got that one right here. That's number 8. So 7, 9, and 10 are straight up killing that precipitate game. What do you think? I think they are. Number 1, I mean, he could try harder, but there's something going on there. I don't know what's going on in there. Let's see. Number 2, clearly. Number 3, let's see. Number 1 and number 3, 2 chlorobutane, and then 1 chlorobutane. So, let's see if we can go ahead and take these guys for a little, take them for a little stroll, take a little bath. Same as these with number 8. Okay. I'll see you over there. Okay, it's been in there literally 5 seconds. I just had to put them in there and then grab the camera. Leave them in there for a hot minute, and then we'll take a look-see. Looks like there's something going on in there, though. I don't know about you. It looks kind of cool, like glowing. Let's see. What is it called? Like aerogel? Something like that. They basically we'll talk about that another day. It's cool stuff though, but a little something going on, perhaps. Yes. I'm at 42 seconds on my clock, so I'm gonna. Yeah, we're gonna hang out for another 10 seconds. How about this? Don't forget that this silver nitrate is added just to kind of allow a precipitate to form so that it's obvious that the reaction did move forward. It's also going to help drive that reaction forward. Once that leaving group leaves, is gone because it precipitated out as silver chloride or silver bromide. And there you have it, folks. So I'm going to take these out and we're going to let them cool to room temperature. We'll take a little look-see, okay? Bye. All right, so there's number 1, 3, and 8. From left to right, 1, 3, 8. And there's record your results. So I don't want you to think that, I don't know what I'll be saying. So let's see. If you see a reaction that does move forward and you don't think it should, then trust your instincts. Okay, so that means there might have been an error, right? But also, you kind of do want to question your instincts a little bit sometimes. So, provided you have studied Sn1 and Sn2 reactions, and you're confident with that, then and you see the reaction move forward, and it contradicts what you've learned, then what you should look carefully at the possibilities of error associated with either something I did or things that were even out of my hand. So, for example, I got these from the stockroom. They're already made, these substrates as well as these solvents and the nucleophile already prepped. And so, who's to say what they really are? No, I wouldn't want to say that. They are what they are, but how clean are they? Is there any source of contamination? And I don't want you to just that's the cop out if you just say, yeah, it was contaminated. That's why it didn't. That's why it moved forward and it shouldn't have. No, that's a reason possibly, but I don't want one reason. I want multiple reasons. I want any and all reasons that you can possibly think of, and I want specifics. I don't want just to say. I don't want you to just say it was human error or no. Stop it. That's ridiculous because you could just say that for everything, right? Oh, it didn't work out because of human error. Well, that's not critical thinking, and we really want to critically think about the Sn1 and Sn2 reactions that we've done in the lab right now, and especially since you're not even here to do it yourself, you need to get the best out of this process. So you need to critically think about why some reactions went forward faster than others, why they went slower, why they didn't go at all, why they went forward and they probably shouldn't have, or why they should have gone forward but they didn't go forward. So any possibilities that may have occurred, I'm not saying that any of those are applicable here, other than the obvious, but I'm just trying to say you got to think. So, yeah. I think that's it, y'all. I'm going to go ahead and clean up, throw my stuff in the proper waste container, and then what do you think I'm going to get? A Red Bull.